All right. I'm going to cover this chapter 13, and then I'll hand out your test, and we'll talk about that quickly. That's my idea. And then I'll hang out and try to answer some of your questions about whatever you want to talk about. All right. Here we go. All right, last chapter. You never thought we'd get here. I know. I don't believe you made it either. All right, so we're going to skip a couple chapters because, of course, we don't have enough time to cover all the goodies that I would love to cover, and I'm sure you're relieved by that. So, the beginning of time, where did it all come from? So, I want to talk about the early history of the universe first. So, when the universe is about 1 billion years old, we have the earliest epoch of the universe. We see galaxies already formed from this Hubble ultra-deep field. That's how far back we can see with the Hubble. The earliest epoch that we can see of the Big Bang, as I just mentioned, was this 380,000 years old photons, when the universe first became transparent. Prior to that, the universe was not transparent, and light could not pass freely, photons could not pass freely without being immediately reabsorbed by another atom, actually by an electron, in fact. So what about conditions before the universe was 380,000 years old? Let's talk a little bit about that. Things will get very strange there. So how do we know anything about the universe before our first observation? Well, we have to use scientific models, fundamental physics, particle physics. We certainly know the universe was much hotter and denser in the past. And using these properties, we can calculate some properties of the early universe. So again, we believe the temperature was much higher when the universe was much younger. So we're going to go all the way back to 10 to the minus 45 seconds after the universe came into existence. So here's an outline of what we're going to discuss. Just to give you some idea, I don't expect you to know all these times and temperatures, okay? I don't expect that. But we'll first talk about what we call the Planck era, when the universe was less than 10 to the minus 43 seconds old. Temperatures were 10 to the 32nd K. You thought that 15 million degrees Kelvin was hot. Yes, it's not. Then we have what's called the Grand Unified Theory era, the Gutt era, 10 to the minus 43, 10 to the 38. And again, these incredible temperatures, and on we're going to go through each one of these stages. Electron, weak, particle, nucleosynthesis, nuclei era, and atoms. And each one of these names corresponds to something important. So the Planck era. Of course, the problem with this is that our theories don't explain this very well because the temperatures are so high, our theories break down at these kind of energies. We do know that it was a radiation-dominated period, so there was probably spontaneous production of matter and antimatter particles, again self-annihilating back into photons, and then popping back out again, and then back in again, on and on and on. It is very, very, very early universe, and its incredible temperatures. Well, we think these energy fluctuations were creating rapidly changing and intense gravitational fields. That wouldn't surprise you. You have a very dense plasma. And probably space and time were incredibly warped. Again, now that we've touched on that just a little bit, that wouldn't surprise you. But again, these temperatures and densities are so high, we don't have sufficient theory to explain them. Why is that? Well, we really need a new theory of everything, as we would call it, that is able to link quantum mechanics, what we know about the subatomic world, with general relativity and gravity. And we don't have a theory that links those two together properly today. A unified one. I'm not sure it would be simple. So, at at this very early time, we believe there was one unified force that described the entire universe instead of the four we have now. Some people believe that supersymmetry, which is an extension of the standard particle model of physics, would help explain that unified force. And here's where that superforce would be. So again, this is a picture from your book where you can see the time here and the temperature. So at that time, we believe that gravity was united with all of the other forces that we're familiar with in the subatomic world. There was some kind of superforce that was in existence at that time, before these other forces came into existence. Okay, the second period, again, is this grand unified period. You can see we call it grand unified because all of these forces were united together. Again, our knowledge of this is not super great, but we believe at this time that there were two forces in the universe. As you just saw, this grand unified theory force, where the strong, weak, and electromagnetic forces were one force, acting as one force, and gravitational force. So again, incredibly early in the universe, and again, incredible temperatures, temperatures and energies that we don't have any way to probe, even with Large Hadron Collider. At the end of this era, a very interesting thing happens. This force will split in two and will become two forces, a strong force and what we call an electroweak force. So the electromagnetic force and the weak force at that moment were one force. We believe at that time a huge amount of energy was released, and we call that period of time, when that happens, the period of inflation. And we believe when this huge amount of energy is released, when these forces become separate, that the universe expands in size extremely rapidly over a very, very short period of time. And that will help us out later on. I think this will show how that works. So here is a hypothetical situation with two objects in this universe. So the distance between them is at the bottom, and they will move in time with the age of the universe, and then, boom, during that period of inflation, they will find themselves extremely far apart from each other, and then at 380,000 years, they can emit photons, because the universe is finally transparent. So that inflation period, when those forces split out, you get an expansion of the universe by incredible amounts. And again, that will help us with some other aspects of our theory, our Big Bang theory. Okay. The third period is this period we call the electroweak period. Not a surprise, because we have this electroweak force now. Okay? Before we had that Guth era, the grand unified theory era. Now we have this electroweak era. Again, very small period of time, all the way up to 10 to the minus 10. This sounds almost digestible, 10 to the minus 10 seconds. Temperatures 10 to the 29, all the way up to 10 to the 15th. Again, that's still a lot. But we have a little better understanding of this period from experimental physics. We can probe this era just a little bit, what we know today. And again, we have three forces in that period, that gravitational force, the strong force, and the electroweak force, where these two had split out during that Guth era and caused that period of inflation. So we have an electroweak theory of particle physics, and that predicts W and Z bosons, which we talked about when we talked about the standard particle theory of physics. So they should come into existence at these high temperatures and energies, and these particles were actually found at CERN, where the LHC is right now, in Switzerland/France in 1983. But again, in this period, the universe is completely radiation dominated. So there's photons running the show. The next period is what we call the particle period. So now we get to some reasonable times, 0.001 seconds after the universe comes into existence. Temperatures 10 to the 12th to 10 to the 15th. And again, we move from a universe with equal parts radiation and particles to a photon-dominated universe, for reasons I'll show you in a second. A variety of particles are created, including quarks, which as we know will be the building blocks of protons and neutrons. And by the end of this era, at 0.001 seconds, all of those quarks will have combined in protons and neutrons. I told you that protons and neutrons are made of quarks. It's not like quarks are floating around there for us to scoop up and check out. You've got to smash these atoms pretty hard in the biggest accelerators on the planet Earth to see the quarks. They spill out for just an instant, and then they go back in. So you've got to reach these kind of energies, these kind of temperatures in order to see those quarks. So these quarks combine into protons and neutrons. We have a lot of baryons. Baryons are basically protons and neutrons. We'll have electrons we're very familiar with. We'll have some neutrinos. And we'll have what we believe some other things that we call WIMPs, weakly interacting massive particles. You don't have to know what that is, but anyway, if we had time to talk about one of those chapters, we're going to talk about these particles. So they're massive subatomic particles that don't interact with matter except in gravitational. That antimatter annihilation I talked about will finally cease during this particle era. So this instantaneous creation and annihilation of particles will cease at the end of this particle era. Okay. So another thing that happens here is related to why we are a matter-dominated universe versus an anti-matter-dominated universe. We would have a photon-only universe if there was not, initially in our universe, an imbalance between the amount of matter and antimatter in the universe. If the universe had been created with exactly the same amounts of matter and antimatter, they would have all annihilated themselves, and we would have a completely pure photon-dominated universe. We would have no matter. Everything would just be photons. We wouldn't be here to observe them. But we know today that photons, for example, outnumber protons by 1 billion photons for every 1 proton. That's an observational fact we can use to figure out where this imbalance came from. So, there are no antiprotons left in the universe today. There's no more antimatter left in the universe today. The only time we can get antimatter is by creating antiparticle accelerators. All right? So what happened to it? So what did exist? The antiprotons that were in that initial universe annihilated with the protons as we understand today, and they created the photons that we see today. Because when you take a matter particle and antimatter particle and you combine them together, you get a shower of photons. So the leftover protons we have in our universe today are left over from that annihilation. So that means there must have been fewer antiprotons than protons in our early universe. And so all of the antiprotons that existed, smaller in number than the protons, they annihilated with as many of those other protons as they could get, and they became photons. Keep protons and photons straight. I know it's hard. And that's why we have these leftover protons, leftover baryons in the universe, but our universe is still heavily photon-dominated. As I said, there's 1 proton for every 1 billion photons in the universe. That tells us something about the original balance between matter and antimatter in a very early universe. Okay. Now we can move on to something we call the nucleosynthesis era. So that's, again, these are some kind of numbers we can deal with. 0.001 seconds to 5 whole minutes after the universe was born. And, okay, now we have 10 to the 9. That's a temperature we can get our heads around, right? 1 billion Kelvin. That's something that we can have some feeling for. So now we have, at this moment, the fusion, you won't be surprised to hear that, of protons and neutrons in the heavier nuclei, hydrogen and helium, also some of their breakup. But because of all of this fusion and this very hot soup in the early universe, that's where all of our helium came from. So, by the end of this period, we're going to have a universe that's 25% helium with some trace amounts of deuterium, which is a nitrogen atom with a neutron, and some lithium, the third lightest element in the periodic table of elements. We're going to end up with this ratio of elements in the universe from this nucleosynthesis here. So this fusion, this super high temperature, allows us to start fusing some particles together. And that, as you know, is essentially the composition of our universe today, except for these trace elements that we get from the stellar cycle. Now, I'll tell you, in the very beginning of this theory, 40 years ago, 50 years ago, before we understood stellar nucleosynthesis, there were people that believed that all of the elements in our universe that we have today were created during this moment. People believe that carbon, nitrogen, oxygen, iron, silicon, everything was created in this nucleosynthesis era. But it turned out they were incorrect. And we know that you can't actually create those elements in this soup for some complicated reasons. So if you read a really old history of cosmology, they'll talk about this nucleosynthesis era as an era where you create all the elements. But that's not the case. We know that the heavy elements are created inside of stars, not in this nucleosynthesis period. Then we have the nuclei era, so from 5 minutes all the way up to that 380,000 which I keep telling you about. Again, going from temperatures of about 1 billion Kelvin all the way down to 3,000 Kelvin. I told you that those photons of 380,000 years left when the universe was about 3,000 degrees in temperature. So again, I mentioned this ratio. This universe certainly was highly ionized. So electrons are finally being absorbed to create atoms, but then immediately ionized by these super hot photons, so they get stripped back off again. But by the end, by the end of this period, it is cooled enough for the atoms to finally be captured by the electrons for good. There's not all these super high energy photons floating around. We're going all the way back to we talked about photons. So if I have X-ray photons or gamma ray photons floating around in huge numbers in this very early universe, I can't form atoms because the electrons cannot stay in those orbitals because these super powerful photons are coming in and saying, no, you can't stay there. Bam! It knocks them off over and over again. It takes until the universe is cooled down to this 3,000 degree Kelvin or around there. So as the photon energy drops to visible light photons, and then they allow the electrons to stay in those orbitals because they're not so powerful that they ionize the atoms all the time. So now I just have normal photons, and I'm back to that kind of business we talked about before, where I have visible light photons coming in, exciting electrons and atoms up into higher orbitals, and they go back down. But I don't have so many photons trying to knock those electrons off. Okay, so we have stable neutral atoms in this period, at the end of this period. And at this moment is when photons can finally freely stream to the universe. Before, they kept getting captured by these electrons. They kept ionizing these atoms all the time, and they kept being reabsorbed and re-emitted all the time. So that's what happens. At this 380,000 years, the first time photons are allowed to travel freely without being reabsorbed immediately. And as I say, those photons, at that moment when the universe was around 380,000 years old, and the surface temperature, the temperature of the universe rather, was about 3,000 Kelvin, is when these first photons were allowed to travel without interacting with other matter. And we can measure those photons. And as I said, those photons have been redshifted, gravitationally, cosmologically redshifted, from a temperature of 3,000 Kelvin, say around 600 nanometers, all the way out to millimeter wavelengths. And we can measure those photons today. That's what the theory predicts, and that's what we measure. It was one of the first predictions, and we have measured it. Okay, so now we have this atoms and galaxies area. That's what we have today. So from the time that those photons were allowed to free stream until today, our universe's temperature changed from 3,000 Kelvin, that's the temperature of those photons when they were first allowed to freely stream, down to 3 Kelvin. That's the temperature of our universe. That's the temperature of those microwave photons today. And the temperature is around 3 degrees Kelvin, and that's why they emit in millimeter wavelengths. So, initially, the universe will have neutral atoms, ions, and electrons with a lot of photons around. We'll have some density enhancements in the universe, allowing the creation of some what we call protogalactic clouds. Stars will form in these clouds. Galaxies will form, etc., etc. After about 1 billion years, all that sort of stuff will happen until today. So again, this is just a chart from your book showing again the Planck era. We don't have a theory of quantum gravity, that's what we call it, that unites quantum mechanics and gravity together, so we can't describe this very well. This Guth era, that's the end of that Guth force, when the electroweak breaks off from the strong force and we get the inflation period. Electroweak period. We'll have the end of the electroweak period by the end of that. Particle era. Nucleosynthesis, how we get the helium and trace amounts of deuterium and lithium. And then all the way down to today. Okay, so remember this chart, basically, is what I would recommend. Okay, again, electroweak. We have some understanding of that from models that we have today and particle physics. This period is much less well understood, but that's the period where inflation will take place. And out here, again, who knows string theory, quantum gravity, quantum loop theory, whatever you want to call it, that's the next evolution. Okay, as I said, there are 2 key predictions from this theory that were predicted before they were ever observed. So that's why we have a lot of confidence in this Big Bang theory. The first, again, as I've already said, we should see the radiation from the end of that nuclei era present today. So we should see those cosmic microwave background photons, and we actually do. They match the temperature that the theory predicts. And the second is we should see some of that, we should see the right ratios of helium and lithium and deuterium abundances that will also match the theory. Okay, let's talk a little bit about the cosmic microwave background because it is super important. Again, it was predicted long before it was discovered. So I've already talked about this. These are photons from the end of the nuclei era. They'll be neutral. They could remain stable. Again, the photons in this era were no longer affected by electrons. We've already said all this. And they have been traveling ever since then for nearly 14 billion years to reach us today. All this is, I've already said all this. So this is how they were interacting before, and then they were allowed to freeze spring once those atoms were able to be created because the temperature dropped. Okay, I've already said this. Came from the universe with a temperature of 3000 K. They should have a perfect thermal black body spectrum like any star. So I showed you those black body spectra before. They look like this, depending on the temperature of the object. And I told you, if you're an infrared human, you're down here, right? Because this is wavelength, this is power. Okay? So again, because of that expansion, the original visible 3000 Kelvin photons should have wavelengths of order millimeters. That's in the microwave region of the electromagnetic spectrum. This is what it should look like. This is what the theory predicts. The theory predicts you should have a curve, just like I showed you, that will peak at around, 1.5 millimeters in this case. Okay? That corresponds to a temperature of around 3 Kelvin. This was originally predicted by this guy, George Gamow. He was working at George Mason University in Washington, D.C. with his graduate students, Alpha and Herman. But they also theorized that this would be an impossible thing to detect. They thought that stars emitted a lot of radiation in the microwave and that you would never detect this signal, even if it existed, because it would be swamped. It'd be noise, it'd be so much other radiation from stars. They said it's not possible. But these Russian guys, Andrei Dorshkevich, I've worked with Andrei. He's back in Russia these days. And Igor Novikov, he's a famous general relativity theorist. They predicted that the spectrum actually was detectable in '64, And they even recommended a particular telescope for doing it, located in New Jersey. These guys, this was 1964, behind the Iron Curtain. They didn't travel very much, but somehow they got a hold, how they got them I don't know, but somehow they got the hold of a Bell Labs Systems Technical Journal that was publishing results about this radio telescope. So they publish a paper in this Soviet journal, which is translated into English, but nobody notices it, that they make this prediction that it is detectable. But at the same time, some guys in Princeton, they also realize, they do some theoretical calculations, they also believe it's detectable, and they start trying to build a telescope themselves. They don't know about the telescope that's actually just about 60 miles away that's actually able to do the detection. But these guys in the Soviet Union know about it. It's really strange. So these guys, they were using that telescope. Penzias and Wilson, their names were. They were astronomers at Bell Labs. They started using that telescope that these guys said should be used for that. They're not interested in the cosmic microwave background. They don't know anything about cosmology. They're astronomers. They're interested in looking at the gas clouds, star forming regions, stuff like that. But in 1965, they detect this noise in their instrument, and they can't get rid of this strange noise, no matter what they do. First, they think it's because there have been pigeons pooping in their antenna. So they clean the pigeons out. They clean the bird poop off. They seal everything up because this is a radio telescope. They send they're nice guys. They're tree hunters. They send the pigeons off to some nature reserve about 100 miles away. 2 days later, the pigeons are back. Turns out they're homing pigeons. So to get rid of these pigeons again, they finally do get rid of the pigeons. And they realize after a while that this noise cannot be from the pigeons and their poop and their straw and all this kind of stuff. It's something cosmic. It's something that's not native to the instrument. It's something in the universe. And one of these guys talks to a colleague about this noise problem. And he says, oh, I heard a talk by this guy at Princeton, and they're building an instrument to build something that's going to detect something around the area that you're observing this noise in that frequency range. So this guy is at Bell Labs. He calls this guy, Bob Dickey, at Princeton, 60 miles away, and says, I got this strange noise in my instrument. Do you know what that is? And Dickey says, that's the noise I've been looking for. Because you detected the cosmic microwave background, which no one thought you could detect. And they weren't even looking for it. So, these guys, here's the telescope. Bell Labs. Bell Labs, I don't know if you know, was the world's biggest telephone company for a while. They were one of the world's richest corporations. If you've ever seen the AT&T building here in Midtown, it's got a big notch on the top of it like this. That was built by Philip Johnson. Basically, they wrote him a blank check. They said, we want a building this tall, and we want it to be a great building. Go for it. It's an amazing building. Anyway, they were filthy rich. They were so rich, they had a research arm. They had astronomers working there. They said, oh, we're going to hire astronomers to work on stuff. So anyway, these guys got the Nobel Prize. They weren't even looking for the signal, and they got the Nobel Prize. The guys that were actually looking for the signal didn't get nothing. They got a nice publication in an astrophysical journal. That's it. The problem is that the Nobel Prize can only be shared by 3 people. And the other group, they didn't know which people from that group should share the prize. Plus there were these Russian theorists who actually predicted that it was possible to detect it. Plus there were those graduate students with Gamma who actually did the first calculations that said it should exist. Too many people. Unless you're the United Nations, you can't be more than 3 people for the Nobel Prize. Because the United Nations got the Nobel Prize too. Okay, anyway. So, first these guys detected with this telescope, but that's not the end of the game. Because these photons are very hard to detect from the Earth's surface. A lot of them are absorbed by the Earth's atmosphere. So NASA launched a satellite in 1992. And they're the first, well, 1990 actually, it took them a couple years to get the data. And they're the first to detect the full body spectrum. And they map that entire spectrum, including its density on the sky. In 2003, those were confirmed by another NASA satellite called the Wilkinson Microwave Anisotropy Probe. And these guys that built the probe in 92, they also got the Nobel Prize in 2006. And I confess that I was at the Nobel Prize dinner when they got the prize. But my wife is Swedish and she got us tickets. I never thought I'd ever go to a Nobel Prize ceremony. It was kind of a live stream in a sense. So it was great, and it was the year that the physics prize was given to astronomers, which is quite special. That doesn't happen very often. So in 2009, yet another mission was launched called Planck. It's a European mission, and they just released their first results earlier this week. 25 papers were published. I haven't had time to look at them yet, obviously. So this is what the spectrum looks like. So the initial points from those guys, Penzias and Wilson, were around here. But since then, they filled in the entire curve, just as it was predicted theoretically, almost perfectly. And this is what the map looked like that they produced. So this is a map of the entire sky, and a kind of an all-sky projection. And you see that this map is a temperature map, and you see there's hot and cold spots in this map. So this is what we would call kind of like a baby picture of the universe. As I said, this is when the universe is 380,000 years old. There are no galaxies in this universe yet. There's no stars. All you have are these free-streaming photons. So this tells you that the universe already was not homogeneous at every point in that very early universe. There were inhomogeneities in the very early universe. And these inhomogeneities are the seeds for all the structure we have in the universe today. These density homogeneities form all the galaxies and all the voids in our universe that we have today. So it's an incredible picture. And this is a low-resolution map. The WMAP map is much more detailed. You can see all of the different kinds of structure in this early universe. And I was hoping to get you a picture of the Planck map, but they didn't have it on their website that I could put up today, unfortunately. I was hoping it would be even more detailed. Even this is hard to see itself, but anyway. Okay, prediction number 2. Why did I lose the top of this slide? I don't know. The helium formation stuff. So, as I said, we should see a certain amount of helium and these trace elements of lithium and deuterium, and we have never found a galaxy that's helium fraction less than 25% of ordinary matter. So that's one confirmation. Because we know that only a small fraction of helium can be produced in the cores of stars compared to the full amount of helium we have in the universe. So that means the original protogalactic clouds already had quite a lot of helium in them, of course. We've already talked about this. The universe had to be able to fuse hydrogen into helium. We talked about when that happened. And then when it cooled, we get this favorable proton creation, and then a proton-dominated universe, or proton plus all those photons left over. Okay, these are just some helium formation details. I think I'm not going to go into this so much. I don't think it's that important. So I'm going to skip this stuff. And this is just a chart showing us exactly what the theory predicts for all these different species, the lithium, helium, and deuterium, and how that agrees with the models. Okay, so quickly, there's still some mysteries that need explaining. First of all, where does the structure in our universe come from? Why is the overall distribution of the matter so uniform on the very largest scales? And why is the density of the universe so close to what we call the critical density? That early episode of rapid inflation I talked about, and I've been stressing, is what solves a lot of these mysteries for us. So the first is, where does the structure come from? Well, we believe that's from these giant quantum fluctuations, which increase the density enough so that we could create galaxies later on. So those density homogeneities we saw in the cosmic microwave background map. Why is the largest scale so uniform? The average density is so uniform on these very large scales. That's probably because inflation helped to equalize some of the temperature and densities across the very largest scales through this radiation exchange, because it was a radiation-dominated universe. So we think inflation plays a really important role for that. And as I say, why is the density so close to the critical density? The critical density is the density you would need for the universe to eventually stop expanding and collapse back in on itself. And we believe it's close to that. This would predict a flat geometry of the universe so that right angles are right angles. And that's another thing that inflation helps us solve. So I think I'm not going to go into this so much because it'll take too long. We can test the ideas of inflation through some ways. Again, this is another one of these WMAP maps of the microwave background. The overall patterns of structure agree, again, with these seeds, and we see that even in the temperature fluctuations and in the structure fluctuations. Again, I said the geometry of our universe, so that's the space-time, we believe is flat, so again, right angles are right angles. There's some theories that say the universe may not be flat, it might have not right angles. We know that 4.4% of our universe, of its total energy budget, total matter budget, is baryonic stuff like us. 27% of the total matter is other things. So we have dark matter, 23% of the total, and then something we call dark energy, 73%. So this is where you're going to find that you're going to believe that astronomy doesn't know anything. Because we understand what 4% of the total amount of matter in the universe is, stuff like us, and we have a lot of observations that point to the fact that there is a kind of matter in the universe that doesn't interact electromagnetically, but only interacts gravitationally. There are experiments now to try to find these particles and measure them and understand their properties. We're also hoping that the Large Hadron Collider will help us solve that problem. And then there's this issue of what we call a dark energy, which is 73% of the total budget, matter budget in the universe. And this goes back to what I was talking about earlier, where I said the very fabric of space is pushing away from itself and causing the universe to expand even faster and faster over time. So this means that the gravitational attraction of all the matter in the universe is not enough to stop the universe from expanding forever, because we have an additional force that's actually in Einstein's equations, which he initially put in for a completely different reason and then took out later and called it his biggest mistake ever. But that there is this extra term in Einstein's equations that predict this extra force in the universe. And we have been able to measure that force by looking at the most distant galaxies in the universe and realizing that the universe is actually speeding up in its rate of expansion over time. It's not slowing down. So that would lead us to believe the universe is going to expand forever and never collapse back into itself. Okay. One last thing. There is one other paradox that I just want to mention very quickly. There was this guy, Olbert, who came up with this question of why the night sky was dark. And it's yet another rationale for the Big Bang. Because if the universe were infinite in extent, unchanging and the same everywhere, if that was the case, then the night sky would be as bright as our sun, because it would be perfectly covered with stars. Think about that. If the universe really is really infinite in extent, this is before we knew about the Big Bang, unchanging and the same everywhere, eventually I would get so many stars piled up on top of each other that they'd be the same. It'd be the same as being at the surface of the sun. We'd have this extremely bright universe. So our night sky wouldn't be dark. We'd have a day sky. So instead of a paradox, you ask yourself these questions. So why is the night sky dark? If I can almost fill up the entire volume of space with stars, I mean the surface area that I can see there in the night sky, I will end up having so much light, it'll be like daytime. It was Johannes Kepler who first realized this dilemma, and he solved it by believing there to be a finite number of stars. He said, well, because this is not true. The universe is not infinite in extent, and there are not an infinite number of stars. Well, he's right. He was right. It's actually true. There are a finite number of stars, but not nearly as few as he imagined. So that's not enough. In reality, it's this fact that we don't live in an unchanging universe. Our universe is always changing in time because it's expanding. So first of all, we only see those stars in their cosmological horizon. And those very distant stars, most of their peak radiation in the visible is not invisible. It's redshifted way out. Think about the light from 380,000 years ago. It was 3,000 Kelvin. Now it's down in the microwave regime. We don't see that light. So it's because of the expansion of our universe that we don't have this Olber's paradox. It makes sense that the night sky is dark because those very distant objects are redshifted out of the visible spectrum. Okay, so I wanted to show a little movie, but I guess you probably want your exams. So why don't I give you your exams, and we can go through that very quickly, and then if you like, I can show this movie. Right. The movie is a simulation of the universe. But maybe I can play it while I hand out the exams. You come up and get your exams if you want. Come up here. I'll put A through G here, and J through E here, and then R through Z here.
No.
Now you get it.